Today I'm going to talk about the paper from the Usenix 2020. It is called the update leaks, the dataset inference and reconstruction attacks in online learning. First I'm going to talk about the membership inference attack. In this attack, we focus on fundamental questions known as the membership inference that given machine learning models and a record, we need to determine whether this record was used as a part of this model's training dataset or not. That, in summary, we want to quantify membership inference leakage through the predictions output of the machine learning models. To analyze these questions, we used to turn machine learning against itself and train and attack models whose purpose is to distinguish the target model's behavior on the training input from its behavior on the input. We want to distinguish the target model's behavior on the training input, and then we want to define whether we can infer this membership from the output. And in other words, we turn the membership inference problem into a classification problems. That whether the output can help us to classify that the input is in the training set or not. And during the studies, we used to investigate these questions in the most difficult settings, that the black box settings, where the adversaries can only access to the model, only access to a black box models and query these models, and also do the inference based on the returns from this model's output. The attackers will first query this target model with a data record, and then obtain the model's predictions on this record. Then these predictions is used to be a vectors of probabilities that the record belongs to some certain class. And these predictions vectors, along with the label of the target record, will then pass to the attack models and help to infer whether this record was in or not of the target model's training dataset. And in the original paper, they used to construct some shadow models that present similar to the prediction of this target model. And then they train the attack models on the input and output of these shadow models. For all records in the training dataset, of the shadow models, the output vectors are labeled as in, and added this attack model to the attack model's training dataset. And they also query the shadow models with they call the test dataset that's disjoint from its training dataset. In other words, the data in this test dataset are always not in the training set. And then the output of this test dataset will be labeled as alt and also added to the attack model's training dataset. So after we having construct the dataset and construct the dataset that reflects the black box behavior of the shadow models, then we will train these attack models and help us to infer that whether the data membership to infer the data membership according to the prediction result from the target models. This is the original define of the membership inference attack, and it is the attack method proposed in the first paper. And now, in this paper, the authors turn to a different model, different learning model, that the online learning models. In the online learning models, there's the original data set that used to train the original target model. And then in the later iterations, there will be some update data that help to update the target models. Then under these scenarios, there comes a questions. Let's look at these samples. We have a probing set, image of 7. We query the target models with this probing set, and it will give us a prediction result. Next, the target model is updated with the update data. Again, we use the image to query the target models at the second time, and then the prediction result is become different. And here it is there comes the motivation that we call this posterior difference can be a new attack interface. In other words, whether we can use the difference between these two query results to help infer the data in this update data, not the original training data. So in this paper, the author proposed 4 attacks from easy to difficult. That's from the single sample to the multi-sample, and from the first label inference task to the data reconstruct task. And here is the general pipeline of the attacks. And here we note that here the difference is comes from the query from the shadow model, not the target model, since we do not in a black box setting that we can manipulate the target model. We can only query the target model. So in the most membership inference attack papers, you are also train a target shadow model to help them do the inference task. However, in this paper, the authors do not draw many attentions on these shadow models constructions. That they do not give any technical details about how they train these shadow models to let them behavior very similar to the target model, because they mentioned that maybe they assume that they know the structures of the target model, because they assume they are attacking some machine learning as a service scenarios, so they can know their structures. And then they also mentioned the previous works that we can steal the hyperparameters from some hyperparameters from the from the target model. So they think that they think that it is very easy to construct the shadow model. So they do not give any details.
Sorry, can you the 4 attacks are the mainstream attacking methods for the membership inference attacks?
Sorry, what?
So you list like 4 attacks here, right?
Yeah. Yes.
So because we don't know, I'm not an expert for this, so okay. Maybe next time if you can put the reference the paper for the for different attacks, it will be great.
Oh, sorry. These 4 attacks are. I will give the details about these 4 attacks in the later.
Okay.
In this paper, the author proposed these 4 attacks.
Okay, so you mean existing membership inference attacks could be classified into these 4 categories?
No. It means that in this paper, the author proposed these 4 attacks in their studied online learning scenario.
So these 4 attacks are proposed by the one paper, right?
Yeah, by this paper.
Okay, and one more question is, we have like an encoder and encoding decoding network here, and the output the information of the it's like the data set, right? The data set of the update. So what is the information of the the update data set?
Oh, okay. So I'm just try to say this. Yeah, for this single sample label inference, this information should be the label inference. So should be the label of this single sample. And then for the multi-sample, it will be the label distribution among these multi-labels. Okay. And for these 2 reconstructions, this information will be the exact these data samples.
I see. Okay, so which means this neural network structure can be used to output these 4 different outputs, right?
Yes.
Okay.
And here for the single sample and multi-sample, that means that in the online learning, we will use different update data to help to update the target model. For the single sample, they assume that in each update cycle, the update data set only contains one single data. For the multi-sample, that the update data will contain multiple samples. That is the definition of the single and multiple. And next, the first is the most it is the easiest one, the single sample label inference. Here, they want to infer. They want in this attack, given a difference. This difference comes from the shadow model. The single sample label inference attacks is defined as to get output vector L. That it is a vector with each entry representing the probabilities of the updating samples affiliated with a certain label. And the attack, and here, since it's the easiest one, is this general pipeline can summarize the attack method. In the first phase, the adversary will generate her attack input. That is the posterior difference. It is the difference. It is the two outputs. It comes from the difference from these two outputs from the shadow models. And then in the second phase, they train an encoder to transfer this difference into a latent vectors. And then in the last phase, the decoder will help to decode the latent vector to produce the this inference vector L. And to train this encoder and decoders, they just use a cross entropy loss, just like this, to do this. So that in the single sample label inference, they just construct a very simple encoder and decoder model to help transfer this difference into a latent vector and try to make these latent vectors can help infer the label. This is their first attack, and they want to use this attack model to demonstrate that this difference can exactly help to infer the update data's information. And also they do the evaluation experiments, and the attack models defined as is A can achieve a strong performance with accuracy of more than 97% on this instance-wide dataset. It is a dataset constructed by themselves that want to classify that predict the salary of different persons. And this to the meanest and the CIFAR 10 is a two very common image dataset. And they proposed attack models can all achieve some feasible attack performance. And here, from the single sample label inference, they will try to do the data reconstruct. That given the posterior difference data, the attack is trying to construct the updated data. Here is denoted as the X. And they want to make this updated data exactly same with the data used to update the online learning model. However, the reconstructing is much more complex task than just predicting the sample's label. So to tackle these problems, they use an autoencoder to generate the data sample in these complex questions. However, different from the attack object, an autoencoder is trying to learn efficient encodings from a data sample. It encodes a data sample into a latent vector, and then its decoder try to decode the latent vector to reconstruct the same sample. However, To face this autoencoder in the attack scenarios, they first train autoencoders and transfer the decoders of this autoencoder to the attack models as the initializations of the attack decoders. To give more details, in the first phase, the adversary will use the Jiadong dataset to train an autoencoder. Here also it is the training set of the Jiadong model. And then they will get latent vectors of this Jiadong dataset. And then after the autoencoder is trained, the adversary takes its decoders and append it to her attack model's encoder. To establish these links, the adversary also add additional connected layer to its encoder that transfer the dimension of this latent vector to the same dimension of this latent vectors. And in the second phase, from the same structures for the single sample, it is just follow the same procedures for the single sample label inference attack, and then he will try to train his attack model. And note that here the decoder from the autoencoder is just serve as the initializations of the decoders, and it will also further be trained together with the whole attack models. In these attack models, the authors announced that they use the mean square error as the loss functions. That is the generated output data, and also it's calculated like this. It is just original definitions. And also they do some evaluation experiments on these three data sets. They construct the two baseline models, named here the label random and just the random. Both of these two baselines takes a random data sample from the adversary's Jiadong dataset. The difference is that the label random baseline picks a sample within the same class as the target updating sample, while the random baseline just take a random sample from the whole Jiadong dataset, not target to the dataset used to update the online learning model. So here the label random baseline can also here they proposed the comparison label random baseline can be achieved by first performing their single sample labeling inference to infer their label and then do the sampling on these labels. And here the autoencoders are takes as the original. The autoencoders here is served as the oracle as the comparison one. That is, since that the adversary cannot access to the original updating samples. Here, so this is just serve as the upper bound of the constructing performance. And here they also provide a visualization of the generated sample. The first flow here, the first row shows the original sample, that is the original updating sample. The second row shows the reconstruct samples by the attack models. And here the third one is the data sample reconstructed by the autoencoder. That's exactly from the updated data sample and generated this. We can see that the construction performance is quite good in the single sample tasks. However, for these two single sample, it is they are just to try to demonstrate that the attack method somehow feasible. And in the more general attacks, they need to focus on the multi-sample problems. Here for the multi-sample level distribution inference, the attacks is very similar to the single sample label inference attacks. The only difference is here, they try to use the KL divergence as the loss functions, since the just the cross entropy cannot measure the difference between two distributions. here, since they want to infer the label distribution, they turn to use this as the loss functions. And for other part of this attacks are all similar to the single sample ones. And this task is still quite easy. Their evaluation result also shows that it is quite good. For this one, they measure the KL divergence. It is the lower the better. That the loss function, the loss is lower the better. And here for this accuracy, we can see that the attack models can always achieve more accuracy than the comparison counterpart, the random. Here I want to explain here the transfer. This is to transfer experiment. But recall that if we want to calculate this KL divergence, we need to exactly know the cardinality of the update data. That we need to know that how many data are contained in this update data. This is also the limitation of this works, and they also add some discussions in the paper, and I will talk it later. So they do this to experiment. That the transfer here, the transfer 10 to 100 means that each of the training sample for the attack model, so the training sample for the attack model is updating data contains 10 data sets, and each of the testing samples for the attack models contains 2 updating data sets containing 100 data sample. That we train our attack models with 10 with the updating data with 10 data with 10 amount, but we use these attack models to try to infer the target models while it updates its target model with 100 data set. So we can say that so for this transfer 100 to 10, that means that it just means it means that they first update the shadow model with only 100 samples, while updating the target model just with 10 samples. So as a result, for these 2 tasks, it is much easier. So that since we update the target, since we update our attack models with more data, but really we want, but the attack target model just update with 10 data. So the attacks can achieve better performance. But however, if the attack models update the target model with more data, while the attack models just use 10 data sets, then the attack models cannot achieve the better performance when they transfer to these scenarios. So this full experiment emphasize that the knowledge about the cardinality of the update data is quite important, so that the attacks have quite important limitations. And next, the last one is the multi-sample reconstruction task. It is the most difficult one. So the decoder here is that here the decoders of this attack model is casted with a GAN generator. And here for more details, first, the adversary sends the difference to the encoder to get a latent vector mu. Then they generate the noise vector z according to the update data from a GAN network. And then to create the generator's output, they concatenate each of the noise vector z with the latent vector mu. And on the input of this cognitive vector, the GAN generated plenty of update samples. And then the adversary will calculate the generator loss as introduced by this equation, and use it to update the generator and the encoder. And here, for this X to G, it represents the samples produced by the GAN network given a latent vector and a noise. And then in the first part of this loss functions is try to measure the mean square errors loss and force the GAN generator to reconstruct all samples in the updated data. However, different from the standard mean square error loss, that the only given a data sample of this updated data, the loss is only based on the generated sample. It's only based on the generated sample, not from all generated data. This allows the GAN to reconstruct the samples in the updated data without having an explicit mapping from the difference to the noise vectors. But however, I still have some questions about the designs in this equation. But however, they said that this equation can achieve the good performance, but do not give some detailed explanations. That is, yeah. So I also cannot give some very rigorous explanation about why it can help to train a better performance of this generator. So for the later part, is try to enforce the discriminator D, ensure that the sample are indistinguishable from the true samples. And finally, we will calculate and update this GAN network, the GAN networks again and again until this generators can give some feasible data, reconstructed data sample. But however, in this part, we can get plenty of data sample. But how can we map this data sample to the different labels? And then here we will use clustering networks. And they assume that the adversary needs to know the amount of the updating data. And then after the GAN is trained, the adversary utilizes the GAN generator to generate a large number of samples. And then they cluster the generated samples to the exactly number of clusters, same to the updated data. And here they just use the k-means algorithm to help performing the clustering test. And in the end, for each clusters, the adversary calculates the central point and takes the nearest samples as the reconstructed data sample. And here they give some visualization samples. We can see that the first line is the original data sample in the update data. And here they show the 5 nearest constructed sample with respect to the mean square error. It is and then after the clustering, they also give visualization on the meanest updating data together with the output of the multi-sample reconstructed test. The left column shows the original samples, and the right column shows the reconstructed data sample. Yet on the on this meanest, their attacks can really achieve some good performance. But for this CIFAR 10, their reconstruction performance are not very good. And again, they also evaluate some mean square error. They also calculate the mean square error and give some comparison counterpart. But however, I think it is not, these results are not very important because anyway, the attack models can achieve the better performance, but lower than the upper bound. Just like this. Or the performance, but for the visualization performance, we can say that for the reconstruction tasks, they are not very good. And then the authors give some discussions about their full attack method. And the first one is the relaxing of the attacker's model assumptions. Since they give two assumptions that the structure of the target and shared models are all the same. And they relax this in machine learning as a service scenarios. And the second one is the data distribution for both target and shared data sets. We assume that these two data sets share the same data distribution. But it is somehow weird that how we can obtain a data set that's exactly same as the original training data set. So they do some traceability experiment that here is the original attacks that these two data sets have the same distribution. And here for this column, these two data sets are not in the same distributions. We can say that the performance is, the first line is the accuracy, the performance become worse. And these four are the mean square error or other KL divergency like this. They also, so the attack performance have become worse. However, they do not give the solutions about these attacks. They only give this traceability experiment. And the second limitation is about the knowledge of the updating set cardinality. And I have emphasized this part for many times. And they also do not give the solutions. And the adversary should need to exactly know the amount of data in their updating set so that they can calculate the KL divergency and do the clustering tasks that are quite big limitations. And third, they discuss about the effect of the target model's hyperparameters. They only target to the updating apples. And here these parameters is the number of iterations that this online learning updated by the update data. They announced that with the increase of the number of iterations, the KL divergence decreases. That means that the inference attacks can achieve better performance. But however, they do not give the explanation. They just mention this. And the last one, that also the target model is thoroughly updated with the new data. However, in some general online learning models, the original training data is updated with the new updated data at the same time, not only with the new data. And they only perform the attacks on the updating data set of maximum of 100 data. So if the amount of data in the updating data exceeds this amount, their performance will drop to unacceptable values. So give a summary. In this paper, they quite do some studies to try to infer the updated data in the online learning models, and from the single to multiple data, and from the label inference to the data reconstructions, they proposed 4 different attack methods. And however, it is just the first step in this online learning membership inference, since they have many limitations. So in my opinion, I think we can do a lot of work in this scenario, try to relax their limitations and assumptions so that make the membership inference become more practical. That's all.